Hello, my name is Mike Wong. It's my pleasure to present our work testing compilers for programmable switches through switch hardware simulation. This is work done at New York University with my co-authors Atish and Amarud. Recently, we have seen the emergence of programmable switches. These switch chips for these devices have offered increased flexibility to network operators, all while maintaining comparative power, cost, and performance to fixed function chips. These switch chips include ASICs, such as Barefoot Stufino and Cisco Silicon One. Additionally, we have seen the emergence of data plane programming languages such as P4, MPL, Lyra, and Domino. However, building switch compilers is difficult. We acknowledge that compiler development in general is hard because you need knowledge of the underlying hardware architecture, and because compilers are complicated pieces of software that require a significant engineering effort. We argue that switch compiler development in particular introduces new challenges because of the constraints of the switch chip. Specifically, we have observed that number one, switch chips have limited hardware resources, such as memory and ALUs. Number two, switches have a pipeline architecture. Thus, computations must be mapped to pipeline stages that respect computational dependencies. Lastly, switches have an all or nothing nature, meaning a program runs at line rate if it can be mapped to the pipeline, or it is rejected altogether and cannot run at all. Thus, because of the constrained computational model of the switch chip, mapping high-level programs to the switch chip instruction set is challenging. This, along with the all or nothing nature, results in compilers having to frequently reject high-level programs even if a mapping exists. We present Druzhba, a hardware switch simulator for testing compilers for programmable switches. Druzhba models the low-level architecture of the switch chip and executes compiler-generated machine code programs, which then allows compiler developers to observe the correctness of the compiler mappings. In modeling the low-level architecture of the switch chip, we primarily focus on the arithmetic logic units, or ALUs, which model the computations on packet headers. We also model packet header vectors, or PHVs, instead of packets. PHVs are vectors of containers, each containing a packet header field. Lastly, we model multiplexers. Multiplexers determine the PHV containers to use for ALU operands and the ALU outputs to use to update the PHV containers. Here is our Druzhba machine model. A PHV enters the pipeline, and the PHV containers are given to the input multiplexers, which determine which PHV containers to use as ALU operands. The ALUs execute, and state storage is read from and written to as needed. Then the ALU's outputs are given to the output multiplexers, which determine which outputs to use to update the next PHV containers. This process is repeated for the remaining pipeline stages. We currently do not model matching, parsing, and scheduling, and leave that for future work. Druzhba has two parts, dgen and dsim. Dgen generates a simulation program that represents the hardware details of the pipeline. We refer to dgen's output as the pipeline description. The pipeline description consists entirely of Rust code. dsim then takes in the pipeline description and executes a compiler-generated machine code program within the context of dgen's generated pipeline. Before dgen can build the pipeline description, we must provide dgen with the hardware specification. This includes the pipeline depth and width and the ALU specification. The pipeline depth and width include the number of stages within the pipeline and the number of ALUs in each pipeline stage. The ALU specification contains the details of the underlying ALUs within the pipeline. This ALU specification is provided using our ALU domain-specific language. Once this hardware specification is given to dgen, it constructs the pipeline description. Optimizations, such as constant propagation, were later applied to the pipeline description generation to reduce overall simulation time. For hardware simulation, dsim simulates the hardware design specified within the pipeline description from dgen. Then dsim takes in as input a machine code program from the compiler. This machine code program configures the behavior for the ALUs and multiplexers. Then a compiler is tested by fuzzing a compiler-generated machine code program with random PHVs from our traffic generator. Let's see this visually. A machine code program is given to dsim. This machine code configures the multiplexers and the ALUs. Then the traffic generator creates a random input PHV, which enters the pipeline. Afterwards, we get an output PHV, which contains modified PHV containers after the machine code program is executed. Here's our compiler testing workflow. Number one, we provide a transactional specification that captures the intended behavior of a machine code program. This transactional specification is obtained by taking the initial input program given to the compiler and converting it to Rust code. Number two, we fuzz both the dsym pipeline and the transactional specification using our traffic generator. Lastly, we check that the dsym pipeline and the transactional specification produce the same output behavior. If the output PHVs from both dsym and the transactional specification are equivalent, we conclude that the compiler mapping was indeed correct. Conversely, if there exists an input PHV that yields two different results from dsym and the transactional specification, we conclude that there is an erroneous compiler mapping. Let's see this visually. The traffic generator creates an input PHV, which is given to the transactional specification and dsym. They both produce an output PHV, and we check that they are equal. If so, we move on to the next input PHV. We repeat this for all input PHVs generated by the traffic generator. If we see that they are all equal, we conclude that the compiler mapping was correct. Conversely, let's consider the alternate scenario. We see there exists an input PHV that yields two different output PHVs. Thus, we conclude that there's a compilation error. We use Druzhba to test Chipmunk, a compiler for the Domino programming language. The compilations of over 120 Chipmunk generated machine code programs were then validated and determined to be correct. In conclusion, we showed how we can model the low-level hardware details of the switch chip, and we showed how Druzhba can simulate compiler-generated machine code programs. This thus allows compiler developers to observe whether their compiler's compiler mappings are correct or not. Thank you for watching my talk. If you'd like further details on Druzhba, please read our paper.